Hi, welcome to our first video about solute transfer and how it relates to dialysis. In this first video, we're going to be looking at conditions of no flow, but in the next video, we'll be looking at what happens when the blood and the dialysate are both moving. To start, let's consider a model of the membrane, a small region of that dialysate membrane, shown here between the two blue lines. On one side, we have blood, on the other side, we have the dialysate, and we have a solute at a higher concentration in the blood than it is in the dialysate, so of course that solute is going to want to transfer to diffuse from the blood into the dialysate. In the thin film model, these concentration gradients between the high concentration and the low concentration are limited to a thin film right next to the membrane. So we have thorough mixing in the blood of the solute, then we have a concentration gradient in that thin film with thickness delta. We have another concentration gradient throughout the membrane. And then on the dialysate side, again, we have a concentration gradient restricted to a thin film, and then we have thorough mixing of that solute on the dialysate side here. So, what is going to happen with this model? Let's make some assumptions. First of all, we're going to assume that we're in steady state. That means that there is no solute accumulating within the membrane. Any solute coming in from the blood side has to leave out the dialysate side. Another assumption is that we have no bulk flow, no ultrafiltration of fluid. And finally, our last assumption has to do with the partition coefficient. And this has to do with the relative solubility of a substance on either side of an interface between two materials. You'll notice here between the blood and the membrane that the concentration is a little bit different. The ratio of those concentrations is the partition coefficient. And we're going to assume that the partition coefficients on the blood side and the dialysate side are the same. So the partition coefficient, alpha, on the blood side is going to be the same as on the dialysate side. So, with that being said, let's think about the flux through one of these regions, one of these thin films. So flux is denoted N, and flux is proportional to the diffusivity of a substance, in this case in blood, and inversely proportional to the thickness of that thin film. And then it's proportional to the concentration gradient. So because we have a condition of steady state, the flux through all three regions must be the same. So we can write a similar equation for the membrane and for the thin film of dialysate. So this is all well and good, but there are several things that we can't really measure here. What can we measure? Well, concentrations that are easy to measure are the concentration in the mixed region of blood and then the mixed region of dialysate. Oops. So, can we somehow combine these equations to only have the concentration in the blood and the dialysate appearing? The first thing we're going to do is use our assumption about the partition coefficients to rewrite this central equation. So the two concentrations there can be rewritten like so. And then, of course, the whole thing could be rewritten over alpha theta m. So, what next? Well, the total concentration difference between the blood and the dialysate is simply the sum of the concentration differences in the different regions. So now hopefully you see that we can combine our equations in terms of a concentration difference that we can measure and the flux. So for example, this concentration difference we can get from this equation. So finally, we can rewrite this equation in terms of a flux, what we'll call filter coefficient, and then our concentration difference that we can measure. So what is K equal to? Well, 1 over K is going to be equal to all of these terms in front of the n's. So my background is in electrical engineering, and when I look at this equation, I think of Ohm's law. I think of a voltage difference, or a concentration difference, and I think of a current, in this case a flux, so that would make this the conductivity. So 1 over K is simply the resistance. And this kind of makes sense to me, because what is resisting the flow? Well, a thicker, thin film is going to make it more difficult for the solute to flow, but a higher diffusivity is going to make it easier. And then we have 3 regions that are in series, and just like resistors in series add, these resistances here add. So here's an equation that we can use in a case of no flow, where we have a filter coefficient relating a concentration difference and a flux of solute. Spec sheets for dialysis filters will have a value for K written on them, but they'll usually be written for certain values of flow of blood or dialysate. In this case, we have no flow. We'll have to go to the next video to see what happens then.